Hello, everyone. Welcome to the Recurrent ETDS seminar. So at this visit time, we have, to our great pleasure, my old and dear friend. Uh, the friend is not old, the friendship is old. You know what I mean. Anyways,
I'm also old.
we have Zemer Kosloff, and he'll be giving us a brief outlook and introduction to non-singular Bernoulli shifts. Which are quite fascinating. Anyways, over to you, Zemer.
Okay, so thank you very much, Nishant, both for the introduction, the friendship, and the opportunity to speak in your seminar. What I planned for this seminar is some kind of introduction to this kind of model of non-singular Bernoulli shifts, which in recent years has a lot of advancement. It's not going to bring to the state of the art of the model, but I kind of want to show the flavor of this model and also to give some flavor of the study of non-stationary ergodic theory or non-singular ergodic theory. So as the title says, it's the model of Bernoulli shifts. The model is a slightly more or even greatly more general than the one that we normally study in ergodic theory. It's just a shift action on a product space, so space of all sequences, equipped with a perhaps non-stationary product measure. So you could just view this as a shift on independent, but not necessarily IID random variables. So this is some kind of the model. And this kind of model would fall in the subfield of non-singular dynamical systems. And by this, what I mean is transformation of a standard probability space, which satisfy the condition that the push forward of the probability measure by the transformation is equivalent to the of the measure by the transformation is equivalent to the measure, meaning that they have the null sets. So if we think about measure preservation, saying that the quantities are preserved over time, this condition just says that the quantities can change over time, but the relevant quantities, the one that have positive mass, this collection is preserved when we iterate with the transformation. Okay, so this is many questions, as I said, have been studied on this Bernoulli shifts, and kind of classical questions like what are the orbit equivalence classes that are possible for Bernoulli shifts. And these, while being old questions, are they only quite recently been resolved. In this talk, I'm not going to go through this, but if this interests you, I'd be happy to you contact me and I can either point to some references or explain some points. Okay, so this is this kind of model. That's what I plan to kind of discuss, is this kind of model and this very basic stuff on non-singular ergodic theory to kind of introduce you to this field in some way. Okay, so let's do a more formal introduction to Bernoulli shifts. So given a sequence of independent A-valued random variables, for the purpose of the talk, we would have A to be a discrete set. It's also possible to take uncountable sets, but for the purpose, we're going to just look at discrete sets. Mu n will be the distribution of the random variable xn, so this is a probability measure on A, and the product measure, product of mu n, is the distribution of the whole sequence when we take it together. So of the whole sequence xn, and this is a probability distribution of this space of A-valued sequences. So why is it called a product measure? And this is because if we take any m tuple of elements in A and any m distinct integers, when we check the probability of the intersection of the events that x and I equals AI, this can be described as a product of the marginals mu and I of x and I equals AI. So this is the terminology for the product measures because of this formula. Okay, so when we have this model, we can act on the sequence space by a shift, as we all have been doing in ergodic theory. So we take Tx at the point j will be x at the j plus 1. So this is just shifting the whole sequence by 1. And if we manage to check that the push forward of mu by t, or mu composed with t, I took this because it's invertible, is equivalent to mu, we can call the shift a non-singular Bernoulli shift. So this is the definition of a non-singular Bernoulli shift. It's a sequence space a to the z with a product measure satisfying the condition that the push forward of the shift is non-singular. Okay, so this is the general model, and just to kind of recast this into the place that we're all most comfortable with. So the simplest and most widely studied examples with the xn are IID, and then the shift is measure preserving, and this model is what is taught in textbooks as a Bernoulli shift. These systems we're going to call IID systems, and we're going to have a special notation for the stationary product measure. This is p to the power z, where p is just a distribution of, say, the null random variable in the zero position. So classical Bernoulli shifts, we know that they are, although they are random, they have many kind of rigid properties. They're always positive entropy. They're always mixing. Their factors by Ornstein theory are always isomorphic to Bernoulli. There's many kind of very deep and foundational results about them, which basically say that they have some kind of a structure that is preserved. And we describe this kind of model of non-singular Bernoulli shift. So there are kind of natural questions one should consider when we start studying this. So first of all, I gave a condition that I said that I want the push forward of the measure will be non-singular for the shift. And checking if something is non-singular is non-trivial. So the question is, can we have some kind of condition on the marginal measures, mu n, which ensures non-singularity for the shift? And if we have such a condition, or even if we don't, can we build examples which are not from the type above of, in some ways, they are essentially non-stationary systems? Okay, so this is a natural question. And if we can build this kind of models, we can ask classical questions as ergodic theories. We can ask whether they are ergodic. We can ask how rich is the possible ergodic theoretic behavior in this model. Does it have some kind of rigid properties like Bernoulli shifts, or it has much more varied behavior? Okay, so this is the kind of thing that the study of this system started. And it started with a very nice observation of Krengel, that the classical theorem from probability theory of Kakutani, one of a fantastic theorem, is relevant for the question of checking whether a shift is non-singular. So let me recall what Kakutani's theorem tells us. So Kakutani studied the following setting. He said, we have one sequence space A to the Z, and we have two product measures on that sequence space. And then we can ask whether they are singular, whether they're equivalent, or whether they have a mixed Radon decomposition. And Kakutani proved the pureness result that either they're mutually equivalent, so they have the same null sets, or they're singular, meaning that they have disjoint support. Okay, and what's even nicer in Kakutani's theorem
there's a question,
is that it actually gives...
Zemer.
What?
There's a question, Zemer. Ananya, you can actually unmute and ask if you want.
So just to know whether A has any specific property.
A is just a discrete set, so either finite set or the integer, positive integer set.
Okay, thanks.
In Kakutani's theorem, you can also take it to be the interval 0, 1, but then the test would be with an integral instead of a sum. Yeah, but so I kind of simplified it. Okay. So again, to go back, when A is discrete, and the two measures will be equivalent. So the first condition we need is, of course, that the marginals are equivalent measures. And for discrete set, it just means that mu and A is 0 if and only if nu and A is 0 for every A in A. So it's kind of easy to check for discrete sets. And after that, what you check is this double sum. So you sum up over all integers, then you sum over all elements in A, the difference between the square root of mu and A and the square root of nu and A, and you take a square. If this is finite, then the first condition of absolute continuity of the marginals is satisfied. And then this is precisely when the measures are equivalent. And just to kind of answer your question again, inside what we have here, some of us who might have studied probability metrics, this is just the Hellinger distance or the Hellinger metric of the distance between mu n and nu n, the inside sum. So when you want to consider the more general cases, you need to assume some kind of absolute continuity of the measures, and then you can also define the Hellinger distance inside, but it will just replace the sum with an integral. Okay. So this is Kakutani's theorem, and why is this relevant for Krengel's observation? Whenever we take the product measure and we shift it, when we shift, we're going to get a product measure where the marginals are just shifted by 1. So instead of mu composed with t, will be the product of mu n minus 1. So if we check Kakutani's criteria, what it reduces to is to have that all the support of the marginal measure mu n is a fixed set B, which is a subset of A. And the second condition is to check the double sum, where nu n is mu n minus 1. And we get this nice convergent criteria. When this is satisfied, this is precisely when the shift with respect to this non-stationary product measure is non-singular. Okay, so is this clear, the non-singularity criteria? Okay, so this is the non-singularity criteria. Let's kind of try to check it with an example. And this kind of example will be in the heart of our result. So for every C positive, I construct a product measure called mu with this upper script C to be a product measure on two symbols, zeros and ones, or say heads and tails. And the marginals, so the probability at time n to see 0 is 1 minus the probability to see a 1, and it's 1/2. But what I do is I add some kind of a bias. For 0, I try to make 0 more probable. And the bias is kind of small. It's a constant over square root of n. And then there is the indicator that I put. The indicator is just in order that this would make sense as a probability measure. So first of all, we need to be able to take a square root. And that's why we take only positive integers. And the condition that square root is n is bigger than 2c, this is just that this number will be less than 1. And so this is the indicator. So up to finitely many numbers and many positive integers, this is 1/2 plus a constant over square root of n. Okay, so it's a one parameter family product measures. And then we can check Kakutani's criteria. So when you check this distance and you kind of look at what you see, you'll get that this is proportional to a constant times the sum of 1 over n cubed, which of course converges. So then we can conclude that this kind of shift that we did this tilt, the slight more tilt to zero, gives us a non-singular Bernoulli shift. And then you can ask, okay, so maybe I gave you some kind of a tilt, but maybe the tilt doesn't really matter, and it's essentially 1/2, 1/2. So the measure is absolutely continuous with respect to 1/2, 1/2. So you can also check, the Kakutani's criteria is also useful for this. If we check the distance between mu and CA and 1/2 the square with the square root, and the Kakutani criteria, we're going to get that it's infinity. It's like sum of 1 over n. And therefore, mu c and the fair coin toss product measure are singular measures. So Kakutani's criteria, this is kind of, I hope that this example conveys how useful it is when you want to try to study these systems. Okay, so this is this example, we're going to see it again.
So, Zemer,
So now before I go,
just to make sure I understand. So in case, we have some muons which such that this is not non-singular, then it just means that it's wandering in some sense, right? The entire space becomes wandering, I guess.
there could be mixed behavior. That's the point of this result, that for some C it will be wandering, and for some C it will be recurrent.
Yeah, but for any C it will either be recurrent or wandering. By Kakutani's result.
This is not from Kakutani. That is from result of myself.
So then can you go back to the last slide? I just want to make sure that I'm not
This
mixing up
one?
things. Yeah, so the first one says that it's either equivalent or singular. So if I shift the muons and it's not equivalent, then you're saying that it's completely singular. So then you would have, the support of the first one would be a wandering domain for that. Wait, okay, maybe I'm mixing up things, but
in order to be non-singular, the support needs to be fixed.
Right.
Because of what you said.
Um,
because of what you said, because if it's non-singular for T, for one shift, it's going to be non-singular for any shift.
Right.
And therefore, the support has to be the same.
I'm still not getting to my question, but maybe I can come to it later.
Okay.
Go ahead.
Yeah. Okay, so what I want to do now is exactly kind of clarify what Nishant was asking. This is basic notions in non-singular ergodic theory. Okay, so recall that the setting of a non-singular transformation is a transformation of a standard probability space, satisfying that the push forward of mu by T is equivalent to mu. So this is a non-singular transformation. And then, like is common in dynamical systems, we write for the quadruplet, we call a non-singular dynamical system. And non-singular ergodic theory deals with the study of non-singular dynamical systems. In a similar way that measure-preserving ergodic theory deals with studying properties of measure-preserving systems. But you might think that the change from preserving the measure to just preserve the class of null sets makes no real difference, but it really does. It's much harder to prove even ergodicity or other ergodic theoretic notions. Some of them don't make sense also. If I give you an underlying non-singular system, there's also much more difficult to obtain structural results on non-singular systems. And the reason for this is because the possible dynamical behavior of non-singular systems is much more varied. And whenever you want to say that there is some structure, there is always a counterexample. So it is different, and one has to take this into account. And I want to show you two examples where the dynamical behavior can be different. And the first example is that we can have a non-zero dynamical system which is totally dissipative. But a totally dissipative, what we have is an exhaustive wandering set W. What do I mean by that? I mean that there's a set W, all of it translates by n, t to the n is pairwise disjoint, and measure of the x minus the part that is tiled by W is a null set. And the example you should think about, say okay, this will be an infinite measure preserving transformation, but you can pass to equivalent probability, but you can take the transformation on the real line that takes x to x plus 1, and then W will be the interval 0, 1, half open, say. Okay, so that's an example that can happen. And if every wandering set is a null set, we say that the system is conservative. And what is important to note, this is a famous theorem called Helmholtz recurrence theorem, is that the system is conservative if and only if it satisfies Poincare recurrence, meaning that for every set A and B of positive measure, when we choose a random point, a mu almost every point in A, so we choose a random point according to mu in A, and we check how many times it will return to A, which is essentially the sum on the left. This will be infinity for almost every point. And then you can have the classical definition of ergodicity, which means that every T invariant set is trivial modulo the measure. And if you want to do this to check ergodicity criteria versus conservativity, then it looks the same. The only difference is instead of choosing almost every point in A, I have to choose almost every point in the whole space X. So let me kind of explain why this is true. If there's no invariant set, then from any set you can get to any set. So I can start in almost every point in the space. I will enter A, and because of recurrence, I will enter it infinitely often. What is important here is that if we talk about transformations of non-atomic measure spaces, if we're totally dissipative, then we're not ergodic. So being ergodic implies conservative. And the converse doesn't hold in general. And as we all know that Poincare recurrence theorem for measure preserving systems, they're always conservative because they always satisfy Poincare recurrence. Okay, so this is one change that can happen. There is another class of systems which are transient behavior or totally dissipative, and they have this wandering set, which Nishant was referring to as a wandering domain, but that's so this is a possibility. And there is a structural theorem, a very important foundational one, which is the Hopf decomposition. And what it essentially says is whenever we want to study non-singular transformation, there are always two sets, C and D, in the space. And T restricted to C is a conservative transformation, and T restricted to D will be a dissipative transformation. So we can always break the space into two parts. One of them is conservative, and one of them is dissipative. And in the Hopf decomposition, the set C is called the conservative part, and D is called the dissipative part of T. And for those of you who haven't seen this proof, this is a very nice use of the exhaustion lemma and measurable unions. So this, if you want to reference Aronson's book in the first chapter, has this proof. Okay, so one theorem which is fundamental for Bernoulli shift, and that's what I was kind of answering to Nishant, is that the Bernoulli shift has kind of a pure behavior. It's either totally dissipative or it is conservative. And this theorem took quite a long time to take. The first result in that direction was by myself under the assumption that the marginals are uniformly bounded away from 0 and 1. It was slightly relaxed by Danilenko. And then all the conditions were removed in a joint paper with Bjorklund and Voss. So there's always a pure behavior, and what's important is whenever we are conservative, it means that we are also ergodic. So there is some this is some kind of a rigid behavior Bernoulli shifts. If they're conservative, they will be ergodic. Okay, so this is a foundational theorem that we're going to use afterwards when we're going to discuss some proofs.
So conservative is somewhere like recurrence, and dissipative is something like transience.
Yeah. So whenever it is recurrent, Poincare recurrent, then it's also ergodic.
And dissipative is like transience.
Yeah. Totally dissipative is complete transience.
Okay.
Yeah. Okay. So just so I could phrase the other result and also give you another example of where non-singular systems may behave differently, we can talk about the notion of ergodic index of a transformation. So we can start with a non-singular transformation x b mu t and an positive integer n, and then we can take a Cartesian product, which is a natural thing to do when we have a transformation. We look at the nth product of x, we take the nth product measure of mu, and we have the Cartesian product transformation, which acts on n tuples x1 up to xn, and by applying the transformation to each point separately. So tx1, tx2, up to txn. And it's kind of immediate to check that if we started with a non-singular system, then the n-fold Cartesian product will also be a non-singular system. And the ergodic index will be n if the n-fold Cartesian product is ergodic, but the n+1 is not ergodic. And of course, we can have a case where all Cartesian powers are ergodic, and then we'll say the ergodic index is infinity. So we look for the first time that we take a Cartesian product and it stops being ergodic. Okay, so when we look about probability preserving transformations, so this appears in Furstenberg work on Samarides theorem, but it's nowadays a classical thing which is presented when you talk about weak mixing systems. So the ergodic index for ergodic probability preserving transformation can be 1 if we're Kronecker systems, meaning that we're isomorphic to a rotation on a compact group with the unique Haar measure. Or we can be infinity when we're weak mixing. So this is the condition of Furstenberg, that you're weak mixing if and only if for every ergodic transformation your Cartesian product is ergodic in the probability preserving setting. Okay, so this is when we talk about ergodic probability preserving transformation, this ergodic index is either 1 or infinity for ergodic systems or 0 for a non-ergodic system. But when Perry and Kakutani looked at this, they've shown examples of infinite measure preserving systems. These can, by change of measure, fall into this category of non-singular systems of arbitrary ergodic index. So their examples are kind of Markov chains, and they used renewal theory. Okay, so this ergodic index, so I gave 2 examples. First of all, we can have transient dynamics, and then when we take Cartesian products, it becomes more interesting when we have not the category of non-singular transformations. And such examples were also constructed by Danilenko for rank 1 systems, for those of you who know what it means. Okay, so let me go back now to Bernoulli shifts and go back to the 1-parameter family of examples that we had before, this tilt of the 1/2 measure. So I showed in my PhD thesis that if I take C bigger than 1, the shift with respect to mu C will be totally dissipative. So if we tilt, say, 2 over square root of n, then we're going to get a totally dissipative system And then Danilenko and Lemanchik asked whether there is a way to check conservativity, and there was a very nice argument of Vass and Val, 2017, and they showed that if you take the parameter to be less than 1/6, then the shift with respect to mu c is conservative. Using the result that we said before, we know that below 1/6 it's ergodic, and above 1 it's not ergodic. And the theorem that I would like to talk about today, which is joined with Terry Soo, is the following. So what it says, there is a constant d. This constant is between 1/6 and 1, such that whenever we look at these Bernoulli shift with respect to this one parameter family, if we're below this constant, the Bernoulli shift will be ergodic. If we're above this constant, then it's totally dissipative. And furthermore, if I fixed a number n and the constant is between d over square root n plus 1 and d over square root of n, then t to the n-fold Cartesian product is ergodic, and the n plus 1 is dissipative and hence not ergodic with respect to this measure. So to summarize the last statement, that what it says is whenever c is within this range, we know that the ergodic index is n. And this answers the question of Danilenko and Lemanchik, whether we can have, in the model of Bernoulli shifts, transformations of arbitrary ergodic index. And this kind of points to the fact that this class of non-singular Bernoulli shifts is also much more rich than the regular Bernoulli shifts, which are always mixing, hence infinite ergodic index. Okay, so this.
So what is the intuition behind this number 1/6?
The intuition comes from the proof, because Vass and Val proved that their proof shows that whenever you are in the range 1/6 and 0, you're ergodic. This d will be the supremum of all constants such that this is ergodic. So the supremum will be above 1/6 because of Vass and Val. And it will be less than 1 because of my result.
What about the endpoints, Zemer?
So we don't know. We don't know what happens at the critical value, and we don't know what is the critical value. This d. We know it sits within a range, but we don't know how to calculate the precise value.
No, but what happens at c equal to d, for instance?
We don't know. The answer is we don't know. If we knew, then that would fix the result more nicely.
So this is like upper semi-continuity or lower semi-continuity of like critical values, like they speak about in phase transition and so on. It seems like that kind of a.
It's similar to the percolation problems that whenever you know that there's a constant of phase transition, then you would want to know what happens at the precise constant, and that will be a different technique than to proving the existence of the constant.
Mm-hmm.
But we don't know yet how to do what happens in the precise constant. That's a very interesting question to check. Okay, so what I would like to do is I would like to kind of sketch you some proofs which are interesting in this kind of thing. And okay, my plan is to show the first part together with the fact that there is no absolutely continuous stationary probability to mu c. And if we will be interested, we can also talk about the last part, but we'll see. Okay, so I'm going to give some proofs on this model. So the first thing I want to show is that there is no absolutely continuous shift invariant probability whenever the constant is bigger than 0. And this proof uses a very nice idea of Krengel, which for those of you who've seen, this is some kind of a use of physical measures. Okay, so let me kind of show the proof. So the first of all is I need to kind of set up some notation. So if I take a finite set F, finite subset of the integers, and a finite string indexed by F of zeros and ones, I can look at the set of all the points X in the full sequence space, such that when we restrict to F, it is like Z restricted to F. And this kind of collection of sets is the so-called cylinder sets in the product space, and they form the basis of the topology. And you write A for the algebra generated by cylinder sets, and this is just finite disjoint union of cylinder sets. So two cylinder sets, either one is contained in the other or they're disjoint. So the algebra is kind of simple, and the algebra can be always written as a finite union of cylinder sets, and this is a dense algebra inside the Borel sets. Okay, so what I'm going to do is I'm going to do a variation of the so-called Hopf method. So I'm going to first check the ergodic theorem for nice sets. So these are C. So I take a cylinder set, and I check what happens for the average of times that we enter the cylinder set. And this is essentially the proof of the law of large numbers. There is independence up to some up to the size of the block, but it's a nice exercise to show that whenever, because the C over square root of n goes to 0, what will happen is that this average will converge almost everywhere to 1/2 to the power of the support of the cylinder set, so the set F. So this is some kind of an exercise on basically you calculate the second moment, and you can calculate fourth moment after you subtract the expectation, and you will see that this is what happens. So it's kind of a weak law of large numbers with Borel-Cantelli. But once we know that it holds for cylinder sets, because this sum is finitely additive, then it's going to be also holding for every set in this algebra of finite disjoint union of cylinder sets. So whenever I take C in this algebra, I'm just going to converge to kappa of C, where kappa is the stationary product measure of fair coin tosses. So just 1/2, 1/2. Okay, so now I know that I have an ergodic theorem for a dense collection of sets, and I want to use this kind of property. This is what I call a physical measure. I want to use this property to show that there cannot be an absolutely continuous invariant measure. So how do I argue from here? So I assume that there is some measure nu, which is equivalent to mu c, which is shift invariant. And then I just do the ergodic theorem for sets in this algebra. Oh, sorry. So what I have is that nu almost everywhere, the ergodic sum will converge to the conditional expectation of the indicator of the set given the sigma algebra of shift invariant sets. And the conditional expectation will be with respect to nu. But because nu is equivalent to mu c, whenever I have an almost everywhere statement for nu, it's an almost everywhere statement for nu c. So uniqueness of the limit, we can deduce that this conditional expectation will equal kappa c for every c in our sets in this collection of sets A. But once you know that, once you know the equality for dense collection of sets, then by Carathéodory's theorem, this is the same measure. So we know that nu is kappa. So if there is a shift invariant absolutely continuous measure, it must be this fair coin toss measure. But we checked before that kappa and mu c are singular. We use Kakutani's criteria. So this is absurd, and we deduce that there is no absolutely continuous invariant measure. So this is some kind of, I think it's a nice demonstration of the use of physical measures in order to verify whether we have an absolute continuous measure. So this is a nice idea of Krengel. What is harder to do, and this has been done in the joint work with Björklund and Voss, is that we show that there is no absolutely continuous infinite invariant measure. And for this, we cannot use the ergodic theorem, so you have to argue differently. But this is kind of the starting point. One of the first results on Bernoulli shift was that if they have an absolutely continuous invariant measure, it must be a product measure, and under the assumption that they have some kind of convergence at infinity. Okay, so this is, we know that they are purely non-singular systems. They cannot be transformed to a stationary system. Okay, so now what I want to show you is how do we prove that the existence of this constant d, which separates ergodicity and dissipativity. And as Nishan said, this is a similar argument that one often encounters in percolation. What we would like to show is that if I have two constants, C1 and C2, ordered that C1 is less than C2, and I know that the top one, the shift with respect to mu C2 is ergodic, then I would like to deduce that the shift with respect to C1 is ergodic. So this is a typo, this should be C1 in this. So what I want to show is that ergodicity, if we know that we're ergodic, then it will go for all the constants below. So in percolation, one argues, usually if you see kind of classical textbooks on this now, there is the notion of monotone couplings. This is not exactly how we do. We argue via factor maps, which I'm going to discuss in the next slide. So instead of monotone couplings, we do some kind of factor maps. They are related in some ways to monotone coupling results, but not directly. Okay, but because we did manage to, we will manage to be able to prove such a result, we can define D, and that answers some of the questions I had before. We just take it to be the supremum of all the constant such that the shift is ergodic with respect to mu c. So because of Voss and Wahl proved that for every c less than 1/6 it's ergodic, then this D will be above 1/6. And because we know that for every c bigger than 1 it's not ergodic, then it's below 1. So this will be the desired D. So what I need kind of owe you to show is how we discuss the factor maps. How do we do the factor maps? And I will show this next. So is the strategy clear? Yeah. Okay, so let me kind of discuss factor maps. So a non-singular system, xb mu t is a factor of a larger system yc nu s. If we can have a mapping from the space y to x, which is measurable, and this mapping will intertwine the actions nu almost everywhere. So this is the condition that we know about factor maps. But what we want is that the push forward of the measure nu by pi will be equivalent to mu. And you can ask me, why don't I ask, like we've seen before, that it equals to mu? So the first reason I wouldn't ask this is because mu is not preserved. There's no reason I should want to have equality of measures. It doesn't give me anything more than just the absolute continuity. If this happens, this is a factor map, and when pi is invertible, it is an isomorphism. And the remark says that if it did preserve the measure mu, then I can just pass to an equivalent measure and reduce to the original factor definition that you've seen. So this kind of definition, when you study just probability preserving systems, it makes no difference. If you can achieve this, then you achieved. If the larger system is probability preserving, then it will imply that the smaller system is probability preserving up to changing to the correct measure in the measure class. So that's not a big thing, but what is important about factor map is that if I have an S invariant, oh, this is wrong, any T invariant set can be lifted by the factor map to an S invariant set. So the rows of T and S in this sentence are interchanged, I'm sorry. And this is what is important here is that a factor of an ergodic system must be ergodic. And the converse is not true. The converse is not true because one can have a dissipative system even with stationary factors. And I might say something more about that. Okay, but this is what is important is if we start with an ergodic system and we can factor it down to another system, then the system on the bottom will also be ergodic. Okay, so this is what we're going to use. And let me kind of show you the instruction. So I take two constant d less than c, and I assume that the shift with respect to mu c is ergodic. So I start by this setting. And then what I would like to build you this ergodic transformation, which will have mu d as a factor. The shift with respect to mu d as a factor. So there is this parameter q, which is d over c. That's just a number that is less than 1. And I look at the probability measure, which is a probability measure on 0, 1 to the z times 0, 1 to the c times heads or tails to the z. So it's essentially a threefold Cartesian product of two symbols on the shift on two symbols. On the first one, we take mu c. On the second one, we take the fair coin 1/2, 1/2 to the power z. And in the last one, we do a bias coin with probability q for 0 and probability 1 minus q for 1. So this is a transformation on the threefold Cartesian product on two symbols, and we can act by the shift on each coordinate as the Cartesian product transformation. And essentially, this is by changing just the alphabet, you can look at this as a shift on just as one shift on the alphabet 0, 1 times 0, 1 times heads and tails. And because the second coordinate and the third coordinate, the shifts are measure preserving, this is stationary systems, then this will also be a non-singular transformation. So S is conservative. Why is this conservative? I started with an ergodic transformation, mu c. Ergodic implies conservative. And if I take a conservative non-singular map and I multiply this Cartesian product with probability preserving transformation, then this will keep it conservative. So this is a class. Maybe I'll kind of explain this later, but there is a criteria to check whether something is conservative, which involves the Radon-Nikodym derivative of the push forward of the measures. And if you look at this criteria, when you multiply by probability preserving systems, that will preserve conservativity. So recurrence is preserved by multiplying by probability preserving systems. Okay, so we know that S is conservative, and it's a non-singular Bernoulli shift. And we can even show that it satisfies this technical condition called the Devlin condition. And this is just that I cite the correct theorem from the three results. It's a conservative Bernoulli shift, and therefore it is ergodic by my result. And now what I want to show is that this S will have mu d as a factor. The shift with respect to mu d is a factor, and the factor map is actually very simple. So what do? We take the factor map, just looks at each value of the sequence separately. So we have X, Z, and R. And I toss the coin, the Q coin. If I get the heads, then I choose the first coordinate. If I get the tails, I choose the other coordinate. Okay, so this is this kind of argument. And then you can check where I say that it's a factor map. So because the coordinates in omega, when I take different j's, they're independent, and I do it only a number, I do it j by j, then I'm going to get a product measure on the bottom. And then I just need to check the distribution of the product measure. And if you carry out the calculation, this is why we chose Q to be D over C. And this will give us exactly this measure mu D. So what we showed, that it's a factor of an ergodic system, and therefore it is ergodic. So ergodicity is closed by taking the constant downwards. Okay, so this is essentially this proof. And I'll be happy to answer any kind of questions which maybe were not clear regarding non-singular systems. So I think I'll probably stop now.